Hello students, welcome to the next lecture on classical electrodynamics, and today we have lecture number 4, and this course is addressed for the MSc students majoring in physics. And today we are going to discuss about the green functions for a linear differential operator, especially with reference to the electrodynamics problem. And in order to discuss this, we need some foundations, and those foundations are we call the prerequisite we already discussed in the last few classes. Namely, that we have seen the Dirac delta function, how to understand the Dirac delta function in terms of a property. That means the Dirac delta function itself can be defined only if you have a well-behaved function. That's what we have seen in the last class. And in the case of the electrodynamics, the well-behaved function is going to be the charge density, for example. So the charge density will be always going along with the Dirac delta function. So as long as the charge density is a well-behaved function, you can perform the integration of the Dirac delta function together with the charge density. So the together with is very important. Okay. So we will see how this is going to work out, and what we have done in the last class, that is already I am showing here. I'll bring the cursor, is not there. I'll bring the cursor. So in the last class, we have seen this particular result, that we have considered a vector valued function which is given by r cap by r square. R cap is the unit vector, of course, and we have evaluated the divergence in the spherical polar coordinate system, got 0 here. And for this expression, we have also applied the Gauss divergence theorem. And on one side, you got the 0, other side, you got the 4 pi. And we would like to know how to merge or how to explain the discrepancy between the two different values, namely the 0 and 4 pi. And we got, of course, the answers which you have seen in the last class, namely the Dirac delta function. Dirac delta function has the ability to switch from 0 to some other value suddenly. You got it? Spiking suddenly. The Dirac delta function will take 0 value all the time. That's what you have here, 0 value all the time. And suddenly it will go to some number here. Here it is 4 pi. Okay. Suddenly it reaches to some number. And practically or theoretically we say Dirac delta function will spike to plus infinity. Spiking means it will blow up to infinity and then return back to 0 once again. So there is a 0 all the time, and suddenly it will go to 4 pi around a particular point, and that point is what we can call it as the origin. It could be origin or it can be any other point. But in our case, for the time being, when we are considering the sphere of radius r equal to 0 happens to be the point of interest, and therefore the origin is the place where the Dirac delta function is going to spike. So we are going to use the Dirac delta function in order to address how to explain the discrepancy between 0 on the left hand side and 4 pi on the right hand side, so that we can see. But before that, I will also explain what is the today's work. So in today's classwork, we are going to learn what is known as green function for a differential operator, especially a linear differential operator that appears in a differential equation. That will be your today's main work. But in order to do that, we need some of the standard results, or some of the expressions. We need the results. One of the result is like this. So this is how the results will look like. Divergence of r cap by r square is 0. So this is one result. Similarly, you can ask the question, instead of divergence, if you take a curl, what will happen? And then you can ask the question, what will happen if you take the gradient of 1 over r square? Okay, r cap will not be there for the gradient. For gradient, we need a scalar. So you ask the question, what is the gradient of 1 over r square? So all these expressions have to be evaluated in the spherical polar coordinate system, because r represents the radius of the sphere. So these kinds of results we need. Okay. In addition to the results from the electrostatics, namely the divergence of the electric field and curl of the electric field. So if you have all these results, okay, if you have all these results, we can formulate all these expressions into one equation, what is known as the Poisson equation in electrostatics. Of course, you may be knowing what is that equation, but now you are basically learning how the mathematical structure is evolving, and how we are arriving at the Poisson equation. That is one story. So once you have this particular Poisson equation, the one thing is clear, that the Poisson equation is a partial differential equation. Of course, you can consider in whichever coordinate system you are interested in. And in particular, we will consider the spherical polar system as one of the main things. You can also consider cylindrical, but let us not consider the Cartesian because that is going to be fairly simple. So we will be discussing with mostly the spherical polar coordinate system, three-dimensional, as well as cylindrical polar. So coming to the green function itself, what is the green function is going to do is that we are addressing the question, or we are addressing to the problem of solution of the Poisson equation. There are various methods are available for solving the Poisson equation, and one of the techniques that is much interesting is a class of problem where green function is going to help to solve the Poisson equation, or in particular any linear differential equation. So green function is not very particular to electrodynamics. Green function is a general mathematical methodology that is applicable to a variety of linear differential equations. It could be ordinary differential, or it could be a partial differential equation. But linear differential equation is one requirement, and the second important requirement is that the differential equation has to be inhomogeneous. Okay, that means the source term should be present. Either you can call by the name source term, or you can call by the name what is another name for that is the sourcing function or a forcing function. Forcing function is also alternate name because this kind of terminology has come from linear harmonic oscillator, where you give the forcing term so that the oscillator will keep on oscillating without decaying or without damping. So that is how the terminology is coming. We call it as a source term because in electrodynamics, charge densities are called the sources. Electric field is called the field. So source is the starting point, field is the consequence. So this kind of terms are coined because of the appropriate physics that you have. So the point to be noted is that inhomogeneous differential equation means a differential equation in which right hand side is not equal to 0. That is the easy way to understand. And usually the right hand side is supposed to be a forcing function or a source term. Both are equivalent terms that you are going to have. So only for such kind of linear inhomogeneous differential equations, we can talk about the green function to the operator. Operator means differential operator. So that is the idea. If it is the homogeneous differential equation, there is nothing like green function for that. Okay, so we are going to ask the question of the solution to the inhomogeneous differential equation. So green function is not the solution. Once again, the point to be noted, green function is not the solution to the differential equation, but green function is going to help you to solve the given differential equation. So it comes as an intermediate step. So that is the story here. So you start with the Poisson equation, for example, and then for the case of the Poisson equation, the differential operator is the Laplacian operator, and therefore you find the green function for the Laplacian operator. And once you have that, using that green function, you actually solve the original Poisson equation. So this is how the methodology or the steps involved. Okay, so we are going to see how this is going to work, and all these things is going to happen together with the Dirac delta function. That is very important. So this kind of problems are useful when Dirac delta function is required. And why it is required, just now I have explained you that when you apply the divergence function to the r cap by r square, and of course why r cap by r square is there, it is coming from the Coulomb's law itself. So when we have a problem where the Dirac delta function is required for such a problem, and we are interested to obtain the solution to the differential equation, there the green function comes into picture. So green function will come into picture whenever there is a Dirac delta function as a source term or forcing function. So all these things, how it is going to happen, that's what we are going to see, and today's class work will be that. So certain small things may look simple or elementary, but that doesn't mean that we are going to repeat something which you already know. You may know what is meant by an electric potential, for example. You also know that electric potential and electric field are related by a simple relation, E equal to gradient of potential. So these things you know it, but now we have to write down in a formal way so that you should understand how the Dirac delta function is entering into picture, and how green function can be obtained for a linear differential operator, or we are going to identify at least how we are going to identify that as a green function. So let us see that, and once you have that, we call the general, or we say that the generalized solution to the Poisson equation, or we say electrostatic boundary value problem. So general terminology should be clear to you. Electrostatic boundary value problem is the terminology. Boundary value problem means you have to specify what is the limits of the boundary. You are not going to discuss from minus infinity to plus infinity, right? You have to define some limits. If you are going to consider a sphere, for example, the sphere is going to serve as the boundary. So electrostatic boundary value problem means when we are writing down the Coulomb's law in terms of its divergence curl, and if you combine the divergence and curl, we will be getting the Laplacian. So ultimately, Laplacian is going to give all information about the Coulomb's law in a mathematical way, and the Dirac delta function is naturally taken care in that particular equation. So this is how we have a mathematical formulation. This is how the equation itself is developing, and the solution to the Poisson equation is what is called the electrostatic boundary value problem in electrodynamics. Okay, for the case of the static. So this is one main topic. And similarly, when we are moving to the case of the electrical current, once again we will be having the magnetostatic boundary value problem. So ultimately, what we are going to study is that we are addressing to the problem of solving the Maxwell's equations. And remember that when we are talking about divergence and curl of electric and magnetic fields, they are ultimately the Maxwell's equation. So this particular course, namely the MSc level course on electrodynamics, will be focused on some kind of generalized solution methodology for the Maxwell's equation. So you can consider either in vacuum or in material media. So we will discuss the material media in the next class. But now we will address to the formulation of or we say development of the equations in appropriately according to the vector calculus rules, and then see what is the green function for the del square operator in the Poisson's equation. So that is our classwork. So let me show the board and then explain now. So this is, of course, you know what this is, and from the last class work, let me therefore write down how we can resolve the paradox, okay, by having the Dirac delta function. It is quite simple. That let us write down the divergence expression. So the divergence of, we can write down divergence of r cap divided by r square will be equal to 4 pi times delta cube of r. So here the point to be noted is that this delta cube of r that is written down here is basically 3-dimensional Dirac delta function. So this particular 3-dimensional Dirac delta function means it is basically product of the 3 1-dimensional Dirac delta functions, which means that you have delta x multiplied by y and z. So delta cube means nothing difficult. It is for each one direction you have to have one Dirac delta function. That's all about it. And this is the this is how you write the final expression and say that we are now in a position to explain 0 on one side and 4 pi on the other side. So therefore, let me therefore write down finally, like what do you mean by writing this is equivalently. Let me write down. We can write down that the divergence of r cap by r square is 4 pi multiplied by delta cube of r. So that is the result that we need, or we say that it's a final result that takes care of everything now. Now there is no more paradox. That's what I'm trying to say. So this being an important result, let me either put a box or highlight that result. So this result is going to tell what information this result is telling is that you are now simultaneously dealing with both 4 pi as well as 0. So that point should be clear. Then only you can understand what is happening here. You can see that you can have either a 4 pi, that means 4 pi at r equals 0, or you can have a 0 at all other places. So that is what the Dirac delta function is going to do. So therefore, the Dirac delta function is going to help us to consider both 0 in one case and 4 pi for the other cases. And therefore, we are going to resolve the paradox in this way. So this is one important result. So therefore, keep this particular result. Once we have this result, we are now in a position to evaluate the divergence of the electric field. So I would like to calculate that, or I would like to evaluate the divergence of the electric field. So I'll write down Let us evaluate. Let us evaluate del dot E. So what we have to do is you put a del operator, then you put a dot, then you write down the entire Coulomb's law, namely the electric field, which is nothing but 1 over 4 pi epsilon 0. Then the integral has to be performed on the charge density. Then you have an r cap by r square function. Then you have a d cube r. D cube r means it is a dx dy dz. That's all. And the integration is performed over the primed coordinates. And here, what is the next simplification is that, for the simplification, you need to remember that script r is a function of r and r prime. That is important. So we are going to see how the differential operator is entering inside. You can see that I am taking the del operator inside. Now you can see that. Now the del will come. So del dot r cap divided by r square. I'll put a bracket so that we are combining that. Then the other terms in the equation is identically same. So here the point should be clear. What we have done is this particular del operator has come inside, which means that the del operator will not affect the integration. Del operator will not affect the charge density. It will affect only r cap by r square. Now, how do you know? How do you know that means? That is why I have written this. Script r is a function of r and r prime. So this is unprimed variable. This is primed variable. Now the integration, you see, the integration has to be connected with the dx prime, dy prime, dz prime. That is the volume. The volume is what we call the d cube r. D cube r means essentially dv, where v can be volume. So therefore, the integration has to be performed over the primed coordinates. That is the meaning of this. The integration is performed over the primed coordinates. Then what will happen to the unprimed coordinate? Means unprimed coordinates will not be affected by the integration. So this is first point. Second point is coming to the differential operator. The del operator is actually dou by dou x, dou by dou y, dou by dou z, and correspondingly you can write down in the case of spherical polar coordinate system, which means that you will be having unprimed variables. So del operator or the differential operator will operate on unprimed variable, whereas the integral will operate on primed variable. And therefore now you are able to understand that this can come only on this, because this is the only term which contains unprimed variable. That is why we are able to combine these two things. They will be they are not relevant for the differential operator. That is exactly what we have written down. And once we have this, we are now ready to simplify, because just now I have highlighted or put a box here, and that result is what we are going to dump. And then immediately we will be getting the answer. So let us see that if you are going to substitute that. So I am simply going to substitute that 1 over 4 pi epsilon naught into then integral over the primed variables, charge density multiplied by that expression is 4 pi into delta cube of r. That's what you have to remember. The expression that just now you got it. And then you have a d cube of r prime. So 4 pi into delta cube of r is the result that we got it just now. And once we have that, we are now ready to simplify. And 4 pi, so 4 pi can be taken out. I think 4 pi can come outside. That I will write down. Then what is left out is you have this 4 pi, I'll make it. So that will come out. Then delta cube, then script r, let me expand. Script r means r minus r prime. Then you have a d cube of r. Because every time this r minus r prime should be remembered. Otherwise you do not know how to simplify. Now that we have Dirac delta function, let us compare with the standard expression that we saw in the last class. So what we know about the Dirac delta function is this. We need to compare with that. So integral over the all range, okay, minus infinity to plus infinity, delta of, let us say that x minus x0. I think x0 is better symbol. Let me write down that. This prime notation we didn't have in the yesterday's class, right? So let us keep the same notation for clarity. I was using x naught there. So then x naught. So this is the result that we had. Now we have to use that result in order to simplify this. So how do you do that is that there is only small differences there. So let us therefore change the order. Okay. We can cancel the 4 pi. Then we get a 1 over epsilon 0. And then we have an integral over primed coordinates. Then we have rho of r prime. Isn't it? So let me therefore write down this expression. This is rho of r prime should come. Yeah, that is the first one. Yeah, here what I want to do is delta cube of, yeah, here this is a place where I would like to explain. There is an r minus r prime is there. So now this is the place where you have to carefully see. Now, how to simplify this is by comparing the standard expression. Now, how this looks like, let us see. The integration is with respect to x. The same x is there here. Do you agree? X is there, same x is there here. Then that x is also here. So these are the integrands, that is the variable under integration. They will disappear after the integration. So because the integration is with respect to x and x will take a number, this is a number. You are going to substitute some limit here. It may not be infinity, but you are going to put a number. So once you are going to put a number, the x will disappear. So x will disappear, x will disappear means what is left out is only x naught is left out. So therefore, that will be an f of x naught. So this is the general rule. This is the general rule for any integral, not only for Dirac delta function. Okay. So in that case, here also you have to carefully see. This is r prime. If this is r prime, then what will happen? That r prime has to disappear. So this r prime has to disappear. And the same r prime is also there here. So everything r prime will disappear, and finally we are supposed to get r here. So we will be getting the row of r would be the answer that we will be getting. It looks good, but there is a small difference. The difference is this is x minus x naught, whereas this is r minus r prime. So what I am trying to say is that this is inverted. Inverted means r prime should come first and r should come here, isn't it? Because whatever is to the first variable is x, the second variable is x naught. Second variable is only coming to the result now. Okay, but here it is not so. No, first variable is coming to the result. Therefore, we would like to have delta cube of r prime minus r. That's what I am trying to write down. R prime minus r into the d cube of r prime. So like this I want to write down. But the question is, can you just like that interchange like this? You can't interchange according to your wish, right? So is it really valid or not? That's the question. This point also we have seen in the last class that from the graph, you have to remember the graph. The graph is symmetric about the y-axis. If the y-axis is the mirror, then the graph of the Dirac delta function is symmetrical. Whatever is there to the left side is to the right side. And therefore what happens is you can interchange them. So a graph is symmetric about y-axis is called a even function, right? So for the even function, you can always interchange this variable and the function is unchanged. It is equivalent to the original function. So this symmetry property of the Dirac delta function is very important, so that you can now we are ready to make use of this particular expression. And if you make use of that expression, we will get this answer 1 over epsilon 0. Let me write down this 1 over epsilon 0, and you know how to simplify. You get rho of r. And that's all. There is nothing else is there. You get a rho of r. So the explanation is now clear. You are now comparing with the yellow color standard result and then writing down the answer. And we got the answer now. So therefore, let me write down final result like this. Rho by epsilon is the divergence of the electric field, and that's it. Let us make this as a result and put some box for this. So in the evaluation of the divergence of electric field, you see that the Dirac delta function is very much involved in the system. Okay, and that is very important because the same Dirac delta function will keep coming. Okay, all along the place. And once this is clear, we will quickly evaluate the curl of the electric field, because that will be much more easier. And we need this result to proceed further to the Laplacian. So this expression is simple because now what happens is that dot divergence is going to curl means we have to evaluate the del cross operator for the function r cap by r square. So we have evaluated divergence, right? Similarly, we'll have to evaluate curl, but curl is reasonably, it is a simple answer, so there is no need to worry. So what all we have to do is we will have to expand the traditional A cross B kind of determinant. But however, the determinant is in the spherical polar coordinate system. So that is the place where you have to be careful. And once you have the expression for this, we can now write down that del cross r cap by r square will be equal to, so let me write down, this is 1 by r square sin theta, determinant of the unit vectors ER, then you have r times a theta, then you have r sine theta times a phi. So the determinant will be like that for spherical polar coordinate system. The other things, derivatives are same, dou by dou r, dou by dou theta, and dou by dou phi. And the corresponding components we'll have to write down. It is 1 divided by script r square. So script r square I'm expanding like that. And that being the scalar, so let me write down like that. And then you have the r into 0 and then r sine theta into 0. So in fact, why this kind of expression r sine theta and r comes here? This is the definition for the determinant in the spherical polar coordinate system. So because del cross is there, the del cross is in spherical polar, therefore this is multiplied by 1 into, so this is actually 1 into r into a theta and r into sine theta. So whatever you are multiplying here, you see 1 is there, 1 into r sine theta. So what is that product? 1 times r, then again multiply by r sine theta, you get r square sine theta, right? That is what you are writing here. That expression will come here. And these are just components of this. So you have 1 by r script r square, that is 1 by script r square. Then you don't have any component, this is only the r cap component. What about the theta component and the phi component? Is nothing is there for our function. That is why this is 0. So the evaluation is of course quite simple. Because of the zeros, this is very simple. So many zeros are there, right? That is theta component. So the theta component is also 0, and similarly the the phi component is 0, which is visible to you. How it is visible, you can see that r cap divided by r square, that is what you have, is nothing but 1 by r square is the component corresponding to the radial, and 0 for the theta and 0 for the phi component. So that is the reason why we have written like that. And because of the several zeros there, our evaluation of the determinant is quite simple, and ultimately we get 0. So you can expand this particular thing and see that the result is 0. So I would like to write the result now. So the result is that the curl of the r cross by r square is 0. And once this is available to you, only then we can evaluate the curl of the electric field. Because now you understand why always we take r cap by r square. That is a part of the Coulomb's law. That is why it is very comfortable for us to use that. The rest of the thing is simple. You simply write down the Coulomb's law there, 1 by 4 pi epsilon naught rho of r prime r cap divided by r square, and then the volume element d cube of r. And as usual, you know what to do. This particular step is very clear, that the del operator will be operated only on this particular thing. Integral will operate only on the primed variable. That is very clear to you. So once you take this one, I get a del cross, but the del cross is 0 there. Okay, so that means the entire thing goes to 0. So our result will be that the curl of the electric field is 0. So hopefully that this expression is somewhat simple, and therefore we can quickly write down. So let me therefore write down like this. Explanation is clear, so I'll finish writing. So that's it. That is the result. So I will put a box or I'll highlight that. So we got the result for the curl also. But there is a small point to be noted. You should there is a point. The point is that the curl is not 0 all the time. Not 0 all the time. So we have to note down, how do you know that it is not valid all the time? So let me therefore make a remark here. We are actually doing the calculation. You remember, we are doing the calculation when the charges are stationary. So that's what you remember, right? We consider some kind of a charge density and then started doing the calculations, and where we did not say that they are moving or fluctuating. That means we are always considering that the charges are stationary. So this point is going behind, without every time speaking. Therefore, what happens is, we can say that the charge density is not time dependent. So what you have to understand here is the following. So I'll explain what you mean by that. The point to be noted is that this kind of equations, namely the formulation in terms of the vector calculus, is based on some experimental observation, isn't it? You first have experimental observation or evidence, and that is what is expressed in a mathematical way. Divergence of E equal to rho by epsilon naught. Curl of the electric field is zero. These things from where you got it. From where you got it means you got it from the Coulomb's law. And similarly, in addition to the Coulomb's law, you have other laws are available in the case of electromagnetism, which are all experimental in nature. Now, those experimental evidence is what we call the physical input. It is not that you close your eye and completely do the mathematics, forgetting all the experiment. That's not possible, right? Whatever vector calculus that we are applying is valid only for the experimental facts that you have with you. Therefore, whatever you do should be compatible with the experimental observation. So the experimental observations and the results that you have, that collection of all experiments for electromagnetism, is what I am saying physical input to the mathematics. Because in the classical electrodynamics for MSc, we are talking about the mathematical foundation based on the vector calculus. But that foundation itself is based on the physical input. So that you should not forget. So therefore, I would like to emphasize here, what are the physical inputs that you have? So you first have a charge density or collection of charges. So if you have a collection of charges, which is a charge density, only then you can have an electric field. This is first point. Second point is, what about the charge density? Is it a function of time or not? That is the question. So in case if it is a function of time, we can say that it is moving or it is fluctuating. Anything can happen. So if you are going to have a fluctuating or moving charges, then we can have a pure electric field, not possible. So you will have to have a mixture of electric and magnetic field, or sometimes you may have to have only magnetic field. So here the point to be noted, if the charges are moving uniformly with a uniform speed, that is called a steady movement, uniform motion of the charge density, then we will be having purely magnetic field. The electric field will not be there. So this you can delete. That is called a steady current. When the charges are moving uniformly, we say that steady current is there. When steady current is there, magnetic field is present and electric field is absent. But that is one scenario. The second scenario is when the charge density is not moving uniformly. That means there are acceleration, decelerations are there, and the number of charges are increasing, decreasing, etc. This kind of fluctuation, acceleration, deceleration is there for the charge density. Then only magnetic field is not possible. You will be having a mixture of both electric and magnetic fields together. Okay, so the point to be noted therefore is that when you are allowing a physical experiment where the charge densities are allowed to move and fluctuate, then in addition to the electric field, you have an opportunity that magnetic field may be present, may not be present. And because of that reason, we cannot say that the curl of the E is going to zero all the time. So you understand what is meant by all the time? All the time means when you perform the charge density is constant in some day, and in some other day you perform with a time dependence, etc. That is what I mean to say. All the time you can't say curl of the electric field is zero. And therefore, the point to be noted is that we have to write down that expression appropriate to what is the experimental setup that you are going to have. If you are going to set up your experiment in such a way that the charge density is zero, you always say that the curl of the electric field is zero. No problem for that. But when you are going to set up an experiment in this scenario, you should not say that the curl of the electric field is zero. So that is the point to be noted. So let me complete this. There is one more experimental evidence that you have. Now let me finish. What is this one? Whenever you have a moving charge density, then we say that this is equivalent to a current density, the usual terminology. This is first thing. Then in addition to that, you also have one more thing. So in addition to all these electric and magnetic fields, whatever we discussed, there is one more physical experiment that is available. So that point I will write down here. Okay, I would like to write what is the name of the law. So this first one that you got, it is known as which is familiar to you, it's the Coulomb's law that you have. So that it is easy to compare. Magnetic field is given by the Biot-Savart. So once this is clear, now you know what is the third one I would like to write. You can tell. So the third experimental evidence is that whenever you have magnetic flux is varying in a circuit, which is represented by d phi by dt, you will experience a voltage in the circuit, and that is the Faraday's law. So what happens is that because of this kind of scenario, now the question comes, the so-called curl of the electric field is 0 that you have written just now. Can you say it is always valid? That's a point to be noted. So I want to tell you that this is valid only for static situation. Static, I will say that electrostatics. Static situation only it is applicable. In other cases, it is not applicable because you have the voltage coming into your system, or you say that the magnetic field also enters into picture. So therefore, we have to modify the equation. Later, we will modify. So for the time being, you please make sure that curl of the equal to 0 is valid only for the electrostatic condition. This point is very important, and based on this only we are going to give the terminology electrostatic boundary value problem that we will see later. That is what we are going to see. So the word statics is very important. Okay, once this is clear, now that we have two results which are important. One is the divergence of electric field is rho by epsilon naught, and second one is curl E equal to 0. Now quickly what you can do is that you recall from the pure vector calculus that curl of the gradient is 0 all the time. Okay, irrespective of whether it is any field, mathematically it is true. That means I will say that according to vector calculus. Okay, irrespective of whether any physics is there or not, this particular rule is always valid. So why we are bringing this equation is that we can now compare. Now let us say 1, 2, etc. so that we can compare. So what do you want to compare is, compare equation number 2 and 3. Because they look similar, right? They look very similar. So you can, there del cross is there in equation 2 and 3. So E can be compared with the gradient of phi. So these are the two things we can compare, and therefore VE can be written as gradient of phi based on mathematics, vector calculus. But you know that what we am trying to say is that we can attach a negative sign to this minus of the gradient only by convention. So what do you mean by that? Let me say by highlighting this. Okay. So now what I am trying to say is that purely based on mathematics, you can always say that the vector can be written down as the gradient of a scalar quantity. So phi is a scalar quantity. You can always write down, and we are going to identify that particular scalar quantity as the electrostatic potential. That's fine. But the question is that how do you write a minus here? So the point is that whether you are putting a minus here or a plus here, it doesn't matter because 0 is there. So this expression is valid whether you put a plus of the gradient of phi or minus of the gradient phi. For both of them it is valid. So you have the freedom of choosing anything. And in the case of the electromagnetic theory, it is a convention that we choose a negative here. And why do you want to choose negative? The reason is that we are going to make a statement that, or we are going to have a convention that the electrostatic potential due to a charge at infinity is 0. So that is the reason. So if any charge is present at infinity, then the corresponding electric potential due to that charge is 0. And because of that reason, this minus comes. So that is the point. Why minus comes is because of that reason. So we are going to define the electric potential based on that condition, that a charge located at infinity will be having 0 electric potential. If that is the starting point for your definition, this minus naturally comes. Okay, which you can verify. Of course, this minus explanation I have done in the BSc level electromagnetism course, which is already there in the YouTube. So you can always verify that. So that is a point to be noted. So once this is clear to you, now we are ready to have one more expression, that consequence upon the equation number 2, we have this particular equation. Okay. So now let me write down what is V. So V is going to be the scalar quantity, and we give the name electric potential, in particular electrostatic potential. So that static also I want to mention that this is valid only for electrostatics. So remember once again, E equal to minus gradient of V is not applicable for dynamic case, applicable only for static case. So this is important. So make sure that you always write down that validity under electrostatics only. For dynamic case, we will see how it will modify. That we will see later. Okay. For the time being, this is the situation. And now we have all these results. So keeping all these results, we are going to do something. So therefore, next what we will do is, let us now write down, we have both electric field and the electrostatic potential. So let us write down what is available based on the Coulomb's law itself. So these expressions are clear. Let me write down and then we want to compare. This is nothing but Coulomb's law. So you know very well how to write. And once you have the electric field, you can also write down the electric potential. So I will write down the expression for the potential according to the same Coulomb's law, V of r equal to 1 divided by 4 pi epsilon naught, the same integral, same rho of r prime. But now what happens is I get a 1 over r. So that is the only thing I am expanding. And then I would like to say that this is d cube r. This is r prime. Okay, r prime. And let us give some equation number a and b. Here the point to be noted is that these two equations are same. What I have done explicitly is that this r, the small script r, is actually the modulus of the r minus r prime. Always that is to be remembered. But I want to emphasize that this is looking like r minus r prime. Here also it is r minus r prime only. No doubt about that. Now what is the difference between these two? You can see that there is a unit vector there. Here unit vector is not there. This is a vector quantity and therefore it is required. And electric potential is a scalar quantity. So here none of them is vector quantity. Rho is scalar. 1 divided by this modulus is also scalar. And this is volume. D cube of x prime only tells you that it is actually dx into dy into dz. Finally, volume is a scalar quantity. And the integration is to be performed over the primed region. So ultimately, this is a definite integral. So you get some number here. That's what it means to say. And the connection between the electric field and the electric potential is given by this. Okay, that means if you are going to differentiate the voltage, I must get the electric field. And that's what you say. I get a 1 over r, right? If you differentiate 1 over r, how much you will get? 1 divided by r, what is the derivative? Minus 1 by r square. So you have 1 by r square, but where is the minus? That minus will take care of here. So therefore, it is quite, you can easily understand that based on this kind of expression, the Coulomb's law can be written in two ways. Either you write it in terms of the electric field, or you can also write down in terms of an electric potential. So that comes about from this kind of an expression. Okay, so the point to be noted is that the expression for the electric potential written down in this particular fashion will be generally applicable for the static conditions, whereas the expression written down for the electric field is generally valid for all conditions. That means if the rho of r is going to be fluctuating for you, then you'll have a fluctuating electric field here. That will be taken care. But that will not be taken care in the case of the electric potential because of the assumption. How did you derive this? This is derived based on the condition that the curl of the electric field is 0, right? Because of that reason, remember that the equation B, this is B, is valid only for the electrostatic. So remember once again, electrostatic condition is valid for B, but A is valid for all situation. Okay, we did not demand anything. If rho of r prime is fluctuating, it will also fluctuate here. But you can also try to give such kind of argument. Here also rho of r prime is there, so the voltage will fluctuate. That's nice. But unfortunately, what happened is this expression that we have written is based on curl of E equal to 0. So that curl of E equal to 0 itself is not valid for electrodynamics. Therefore, we don't want to consider this to be a general expression for the electric potential. So that's a point. That's a very important point that you'll have to note down. Okay. So once you have this kind of expression for the time being all under electrostatics, we are going to give some importance to the term 1 divided by r minus r prime. So this term is very important now. That is going to be the term that is going to play a role in the so-called green function. Okay, so always remember that there is a function 1 over r minus r prime. So let us proceed further now. I'll move down. What is the equation number? Okay, B 1, 2, 3, 4. You remember, right? 1, 2, 3 is there. And once we have this, we will evaluate the divergence of the gradient. So once again, purely based on the mathematical reasoning, we can always evaluate what is the divergence of the gradient. And what is the interest behind that is, By definition, it is called a Laplacian. What is Laplacian means? Divergence of gradient, mathematically. So that is why we are interested to evaluate. And it is one line. Okay, let me simplify there itself. It's quite simple. We can now substitute the expression divergence of electric field, but there is a minus. That minus, I'll put it here, minus of del square V. So which means that rho by epsilon naught we already got. So the answer is therefore minus rho by epsilon naught. So equation number 4, is it okay? 1, 2, 3, we remember 1, 2, 3 was there earlier. We can give equation number 4 for this, and okay, this is a result to put a box for that. So quickly we got the expression for the Laplacian of the potential. And once again, remember how you got all these things we got from the divergence curl. Okay, therefore divergence and curl is very important. And remember that the expression for the potential is important. So this is the place where you have to give focus your attention, namely the current equation, which is equation number 4, and the previous equation number B. We are going to compare and write down a very important statement now. Okay, we are going to compare. What are you going to compare is equation B and then together with equation number 4. So why do you want to compare these two equations? That is a point. So let me first write down what you observe. Okay, so by comparing, what do you get? We get the following, right? We get the expression which is given. Let me write down this. So what I'm trying to write, you can see expression will given by will satisfy means. Let me first explain. Okay, then you can see what we are trying to write here. If you look at equation number B and equation number 4, what is visible? Something should be visible to you. This is a differential equation on V, right? Suppose if you take this particular expression for V that is there here and a substitute here, take this and substitute here. There is a differential operator, there is an integral operator. So anyway, you can simplify. Finally, after simplifying, what happens is you are supposed to get minus rho by epsilon naught. That is what it means to say. So what is the meaning of by comparing this to is, suppose if you are taking the entire expression and substitute in this place and simplify, we must get minus rho divided by epsilon naught. That's the meaning. That is what it is looking like. And therefore, we can say that equation number B is going to satisfy equation number 4. That's what I'm trying to satisfy. Okay, satisfy means if I substitute that, left side also I'll get minus rho by epsilon naught. Right side, it is already there. We say that this is satisfying that equation. This is one way of writing. The same story can be written in a different style. How do you write is, if you solve, this is a differential equation, right? Del square is a differential operator. On a Cartesian system, you can say dou square by dou x square plus dou square by dou y square, etc. You can always write down this in spherical polar also. Whatever be the case, this is a partial differential equation. And now you can solve this. Okay, you can solve a partial differential equation, and if you solve it, what should be the answer? You can ask that question. Now we can we can tell the answer that we are supposed to get this expression as the answer. That is, if you solve equation number 4, our solution should be equation number B. But we have not done any solution. But without doing all the solution methodology to the Laplace equation, we already have the solution. That is a point that I'm trying to say. Okay, because we are playing around with the Coulomb's law and then doing the calculation for the divergence, curl, and then based on that, we now are in a position to say that the solution to this particular equation is already there here. Okay, and remember that the equation number 4 is also valid for the electrostatic condition, and therefore a problem of solving the equation number 4 is known as electrostatic boundary value problem. It's a boundary value problem because differential equation will have to provide a suitable boundary condition. That is why it is called boundary value problem. If you say equation number B contains an integral. We don't call it by a term like boundary value problem, even though this is a definite integral. Of course, this is a definite integral because limits are going to come here. So these points are clear and the terminology is also clear, and I am basically writing the two styles of expressing the same information, that equation number B will satisfy equation number 4, or equivalently, the solution to the equation number 4 should be equation B. So this idea is clear, then we will write down. The rest of the thing is clear. So the solution to the equation 4 is given by equation number B. And that's all about it. And then what is the name of the equation if you ask the question? So this equation B, from where you got, of course, these things you already know. Maybe I will write down once again. Equation number B is coming from Coulomb's law, right? So I'll write down that also. So equation B is coming from Coulomb's law. Equation 4 is known as Poisson equation. And you'll have to pay the attention to the 1 over r minus r prime. Okay. So that is one thing. I will also highlight that. I want to make sure the static condition all the time. So it is static, static, static. Okay. Only then it is valid. And where you have to focus your attention is 1 over this term. I'll put a circle or something like that. You'll have to pay the attention to the 1 divided by r minus r prime. So this equation you have to remember, because the board is full now. I will rewrite this particular equation once again in another place in the board. Okay, let me go somewhere else. Okay, I would like to write down the same expression for the potential once again. So simply I'll write down. Now I want to emphasize on the 1 divided by r minus r prime. So I would like to highlight there, because that is the place where you have to focus your attention, and we are going to call this by a special name, capital G of r comma r prime. Okay, so what I'm trying to say is that, how do you know that means? It's a function basically, right? This is a function. So whether you call it by the name f of r, g of r, whatever you can call, but it is traditionally it is called g of r. And you see that r is also there, r prime is also there. Of course, the modulus is there here. It's a modulus, right? It's a scalar function. So the point to be noted is that this particular g is a scalar function. So you should not put a arrow on top of the g. Okay, but it is a function of r vector and r prime vector. That is what we mean to say. It's a function of both. So two variables are required here, and the integration will be carried over by the primed one. And after finishing the integration, we will be left out with unprimed variable as your answer. So that unprimed variable is there. This is your answer. After finishing the integration, all r primes will disappear, and what is left out is only r. That r is there here. So this is the property of the integration. And we are going to give this particular function by the name capital G. That is the point which is interesting and to be noted. And therefore, what happens is, if you are going to use the capital G, now we can write like this. And now we can see that this is how the expression is going to look like. And let us see what is the name of the function. So let me write in a different color. So we will call capital G of r comma r prime by the name green function. So this is called green function, even though I am writing in pink color. And remember that this is valid for the Poisson equation. Okay, so remember that green function means not all the time same. It changes from problem to problem, but since we are discussing the Poisson equation solution, the green function is corresponding to the Poisson equation. So I highlight this particular expression. The potential expression written is valid for the Poisson expression. So this is how we are going to write down the conclusion now. The conclusion is like this. I will write down. So first I will write down conclusion. So what did you determine is the electrostatic potential capital V, right? So therefore electrostatic potential can be determined by, that's what we determined. How did you determine is determined by a function, or whatever the generalized function, what is known as the green function technique. So that is how it is visible, right? How it looks like, first of all, and that is same thing we are writing in a statement. You see, what is the statement that we are writing is electrostatic potential is determined. Where did you determine means it is there here. Electrostatic potential is determined. Is determined means if you evaluate the integral. So how will you determine is using the green function technique. So if the green function is available to you, then put the green function here, and rho of r prime is something that you already know because you are going to start the experiment means you know what is the charge density you are going to keep, and you also know how the charges are distributed. This is the volume over which the charges are distributed. So rho of r prime is known to you, volume is also known to you. Then what is not known to you is what is the green function corresponding to the Poisson equation. So therefore, remember that we are going to say that whatever green function that you have is corresponding to the operator in the Poisson equation. What operator is there means del square operator. If you go to a different equation, then you'll have a different green function. That is important to be noted. Point to be noted. Green function will change when operator changes. So therefore, what you understand from this equation is, highlighted equation is, that we can determine the electrostatic potential using the green function. That's all about it. So the question is that what is the green function for our problem is, it's already written here. It's already written here, 1 divided by r minus r prime. So it is, we are so fortunate in the case of the electrodynamics problem that the green function itself is readily available to you. That is an interesting point. Okay. So let me therefore continue this conclusion. So this is the main conclusion that you have based on our work. By doing divergence curl, finally what happened is, this is what happened. Conclusion is this. Let us discuss more about the green function after doing some small calculation. Okay, we will understand the green function little better, but before that, let us evaluate the gradient, because always we have evaluated divergence and curl, right? After divergence and curl, we will evaluate the gradient. So gradient of a scalar 1 over r. Well, let us this is script r. I think let us first evaluate for the usual r. Okay, then we can always convert it. So okay, so gradient of a scalar, that's what we will evaluate. Once again, it is simple. In 1 minute you can evaluate. So the gradient of the scalar u is given by ur ar plus 1 divided by r. Then you have u theta a theta cap plus 1 divided by r sine theta into u phi a phi cap. Of course, these things must be familiar to you. It's an expression in the spherical polar coordinate system. So once again, remember, spherical polar coordinate system, you can say r cap, theta cap, and phi cap as an alternative notation, but we are comfortable in using ar, a theta, and a cap. And what is the meaning of ur here? I already explained in some of my previous video. Ur means u is a scalar. If u is a scalar, ur represents partial derivative of u with respect to r. That notation is very important. U notation is what we are using. If you don't want to use the u notation, you can use some other notation, no problem. But you have to remember that particular expression. This is easy to remember. That's why I always write like that. ur doesn't represent r component of u. Not like that. You cannot ask that question, r component of u. There is no component. U is a scalar. 1 by r is a scalar. There is no component. So therefore, it cannot represent r component, theta component, phi component. Then what is ur means? Ur represent partial derivative of u with respect to r, partial derivative of u with respect to theta, similarly partial derivative of u with respect to phi. Now the question is, what is u? U is there here, right? 1 by r. So 1 by r is u actually. Therefore, r derivative can be done. Theta derivative, if you do, what is the answer? There is no theta in this expression. Therefore, if you perform differentiation of 1 by r with respect to theta, I'll get 0. Similarly, if you perform the phi derivative of 1 by r, once again, this is 0. So because of this reason, evaluation is fairly simple. So we will write down the result now. So take the r derivative of 1 by r, then you put a unit vector, then plus the rest of the terms are 0. And that's it, you got the result. So let me therefore write down the final expression like this. So our final expression is gradient of 1 over r is given by minus r cap divided by r square. So here the point to be noted is that the usual r is now converted to the script r, and you know what is script r? Script r is r minus r prime, and the primed variables will not be affected by this del operator. As you know that the del operator will operate only on the unprimed quantities, and therefore whatever is written here is valid here also. So that change in the symbol should also be taken care now, and now this is the final result that we have, and therefore let me put a box for this. Okay, so already what you have, this is the gradient, but already you have something, right? So let us compare that. So what is that you already have? We have the expression for the divergence. So let me therefore write down the divergence of the r cap by r square is equal to 4 pi times the three-dimensional delta function. Okay, we'll let us some equation number. I don't want to see the previous equation number. Let us call this by some equation number A. Now once this is ready, we can evaluate the divergence of the gradient. So that's what we are interested in. So let us therefore compare this and then quickly write down how do you write the divergence. Divergence of this quantity is minus gradient of 1 over r, that is there from equation A, which is equal to 4 pi times del cube, or we say Dirac delta function. So you can now understand that we are combining the equation A and the previous divergence result, and this is the final result. This is the final result. Del square of 1 over r equal to minus, that minus goes there, so minus 4 pi del cube of r minus r prime, and that's all. So I'll put a box or I'll highlight this. This is another important result that we have. And in this result, once again, make sure, or at least remember, because I didn't write r minus r prime, so let us explicitly write down that script r. I am talking about the script r. I'll write down that script r should be remembered as r minus r prime absolute value, that is a scalar. So if you want to explicitly write like that, I will better write down once again. So that is an absolute, right? Vertical line, close bracket, then okay, then equal to the right side, minus 4 pi del cube of r minus r prime. Now what do you know already? What do you know is that you already remember what is 1 divided by something. That is your green function. So I can now write down that this is g, and the rest of the thing is same. So now you see that suddenly green function is entered into picture in this kind of expression. Therefore, this is another important relation which is now required. Because this is also del square operator, right? That's what I'm talking about. Poisson equation is del square operator. This particular equation number 5 is also del square operator. So, what you understand from this equation number 5 is that green function is somehow related to the Dirac delta function. Is somehow related to the Dirac delta function. That's what you understand. Now, how do you understand is directly visible, right? This is a green function here. There is a Dirac delta function here. So you have some kind of relation is there between the green function and the Dirac delta function. If the Dirac delta function is not there into picture, green function will also not there in the picture. Okay. So irrespective of what problem you are going to solve, whatever be the case, the point to be noted is that the green function will be connected to the Dirac delta function. Whether it is 1 dimension, 3 dimension, whatever be the case, this is true. Because this vector quantities represent 3-dimensional quantities, delta function is also 3-dimensional. That's all about it. That is the 3 that represents. So anyway, the arrow will take care of the 3-dimensional nature. This is the first point. Second point is that the green, this particular g is a scalar function. I already told you. So let me therefore write down that the green function is a scalar quantity. So once I write that, we can make some comparison with the Poisson equation. So the point to be noted is that the Green's function, what is written down as capital G of r comma r prime, is a scalar quantity. So that is one thing. Now once this is clear, as just now I told you that equation number 5 is looking like Poisson equation because of the del square. It would be better if you can compare with the Poisson equation. So let me write down the Poisson equation itself. So it is, you know that it is a del square of the voltage whatever you have is given by the right hand side is, bracket is not coming, that is equal to, you have a minus rho divided by epsilon naught. So that was the Poisson equation you have for the electrostatic potential. I am writing side by side. Equation number 5 is already there, and the left hand side in the pink color you have the Poisson equation. We are comparing because they look very similar. This side also you have a del square operator, there also you have a del square operator. Right hand side you have a scalar function. This point is clear. So it must be clear to you that the right hand side, this entire thing is a scalar quantity. And here also you have a scalar quantity. Here also you have minus. Here also you have minus. This G is a scalar quantity. That V is a scalar quantity. So you have a del square operator, same del square operator. So this particular equation looks very similar to the Poisson equation itself. So basically, we say that this is a Poisson equation for the Green's function. And therefore, what we understand here is that in the process of solving the original Poisson equation, this is what we say original Poisson equation, in the process of doing that, we reach an intermediate step. Okay, solution doesn't come in one step, right? You have to do several things, then only a solution comes. So while doing the solution to the Poisson equation, we reach one intermediate step or a stage, intermediate stage. What stage is that? Is you remove the quantity under consideration and put a Green's function. This is the general situation happening in all the time. What is happening is the original unknown quantity. What do you mean by unknown quantity is, this is the quantity to be determined. You must understand this first of all. Del square is a differential operator. V is the dependent variable. That means the variable to be determined. What is known to you? What is known to you means charge density is known to me, and then epsilon 0 value is known to me, and then you have a minus 1 here. These are the things I know, and therefore these are the known quantities. And the independent variable is the R vector. Position is the independent variable. There is an independent variable. These are the known quantities or the sourcing term, and you have a quantity to be determined. So what is the intermediate stage is that the quantity to be determined will be deleted, and in place you put a Green's function. That is the first replacement. The second replacement is the right side you have to replace by a Dirac delta function. That's all about it. The right side, entire right side, delete it. Entire right side will be replaced by a Dirac delta function. You don't have to worry about this constants, okay? Anyway, constants, if 4 pi comes, you can adjust here. Not a problem. But the point to be noted is that the entire right hand side has to be replaced by a Dirac delta function. This is always the general story whenever you want to solve a differential equation using the Green function. So you understand what is the intermediate step? Equation number 5 is the intermediate step in the solution of a particular differential equation. So this particular general procedure, you please remember that remove the quantity, that is unknown quantity, and put a G. We do not know what is G. Okay, that is a point to be noted. We do not know what is G. And then right hand side you keep a delta function and then solve this equation. So if you solve equation number 5, what will you get? The solution to the equation number 5 should be the Green function. And that Green function we will be using to calculate the V here. So it's a kind of a roundabout procedure. Instead of solving the original equation, you first solve some other equation. That some other equation is equation number 5. And after that again you come back here and solve this. So generally, you see, solving the differential equations is not a simple thing. It's always a lengthy procedure. So the intermediate step is this methodology is what is going to be found to be an interesting and successful method in solving some of the differential equations where other methods don't work. Okay, for Poisson equation, of course, you have some other methods working, but especially when the troubles are coming, like spiking means reaching to infinity at some particular point. When certain situations happen like that, the Dirac delta function will help, and you know that the electric potential will go to infinity at the origin. You can't calculate electric field at origin itself, because that is the place where charges are there. So at other places you can do. So therefore, in such a situation, delta function will help you. So this is the reason why green function, first of all, is entering into picture, and how green function is related to the Dirac delta function. So you will feel more happy if you can relate, or if you can understand how the green function and the Dirac delta are related, in what way it is related. That is first question. Second thing is, after finding the green function, how to go back to my original electrostatic potential. From here to here, how to move. So if you have this connectivity, then it will be you'll be happy to understand this methodology. So therefore, I would like to explain further how these connectivities are there. So you should understand what we are doing, because things are a little lengthy. First of all, I want to explain what is all happening there. So let us make a conclusion of what happened till now. So the conclusion, what happened till now, is the following. We can obtain the generalized potential, or we say that the electrostatic potential, using the green function method. So till now, this is our understanding, that if you want to calculate, or if you want to find the general solution, this terminology I do not know. General potential, do you understand? I would like to explain what it is. So general potential means there is nothing like general potential. The meaning is that it is the general solution to the Poisson equation. That is what I mean to say. Okay, so whatever I explained, I tried to write that. But however, the statement may not be clear, because how it is given in terms of green function, that connectivity, you may require little more explanation. So I would like to make little more explanation to that now. So the question now therefore is clear. How to understand that the green function capital G is related to the Dirac delta function. So that is a general question. But however, in order to understand certain things comfortably, I will explain the methodology in one-dimensional case, so that you don't have to worry about three-dimensional one, because this is 3D, right? So always 3D will be difficult. So I would like to consider a one-dimensional scenario. In one-dimensional, how do you write the green function? It is simple. G of x comma x prime. So x means we can say one dimension where vectors are not there. Similarly, the delta function also x. So you agree, right? There is no vectors here. So we don't put any vector here. So which means that these are only one dimensional in nature along the x-axis, for example. So that it will be easier to visualize what it is. And this is the scenario. Now what you do is that consider a particular differential equation that looks like this general differential equation, looking like a linear operator. I have some kind of a linear differential operator L operating on some function y of x, will be given by some known function f of x. Right. So this kind of terminology should be clear. So let me write down the capital L represent the a differential operator. It could be anything. Take for example d square by dx square. That's an example. You can always consider that as an example of a differential operator. So once you have this kind of expression, then formally how can you write it? So that's what I'm trying to say. If that is the case, y of x can be written as L inverse of f of x. Okay, you can quickly say what is the meaning of that. The meaning is inverse operator. It is inverse operator to the original L operator. So to the original L operator, And this is how it is known as formal representation. We say L inverse means this is how it is formal representation. Now here this point to be the word formal is very important in the sense L inverse means we can't say that this 1 to the power minus 1 and you should not write 1 divided by of d square by dx square. That is not the inverse. That is not the inverse, right? You understand what is meaning of that. So if you take sine theta, you take a simple example. Sine theta is there. What is the inverse function? Do you agree that it is 1 by sine theta? 1 by sine theta is not the inverse. Then what is the inverse? It means sine inverse of theta is the inverse. So inverse doesn't say there is 1 divided by of that. So there should be totally a different function called sine inverse of theta. That will be the inverse function to the original function sine theta. So not 1 divided by. So therefore, only for some simple situation we can always find like sine inverse theta. For this you cannot find. You can't. How can you write what is the expression for the inverse operator means? There is no way to write down what is in inverse operator. So this point should be clear. What is the inverse operator to d square by dx square? There is no way to write down. When such a situation happens, you still write down the L inverse like this. That is called formal representation. Formal representation means schematically you say that there exists some inverse which we do not know how to write, but even though we do not know how to write, there exists an inverse. That is the meaning of this L inverse. And basically what it means to say is that what should be the inverse operator to a derivative operator means it should be an integral operator. So to that point is clear, right? So L inverse must be an integral operator so that it will act as inverse to the derivative. But however, we do not know exactly how to write that. So this is what is known as formal representation of inverse L inverse. So let me therefore write down this. So our conclusion is that by keeping this, we will write down that L means differential operator. Then we understand that L inverse must represent some kind of an integral operator. So once you understand that this is an integral operator, let us now write down something like an integral. And here something has to come, that f of x is anyway there. Then there should be a dx, but we do not know what should be there. It's an inverse, right? So inverse operator should be an integral of something. So that something is what we do not know. And now we are going to call that as the green function. So it should be an integral operator. So integral of something operated on f of x prime should give you the answer. So we are going to call that thing as the green function. And there is a name given to the quantity inside the bracket, whatever is the bracket, and we will call that by the name kernel. It is a standard terminology in integration. So whenever an expression comes there, okay, to operate something, that is called kernel. Kernel means the quantity that is there, which will operate to the function to perform the integration. So now you are now able to understand that the inverse operator is an integral operator. The integral of something should be there, right? That something is called the green function. We are going to give the name green function, that's all. What is green function? It is to be determined yet. We are going to give the name, that's all, for the time being. How to determine green function, that we will see now. So now that we have these two equations, we can know what we can find from these two equations. Let me write down the general solution to the original equation. Let me write down what is the conclusion now. The general solution to the differential equation number 6 is given by 7, but 7 is given in terms of green function, and green function is for the operator L. Okay, in terms of green function, but green function itself is the corresponding to the operator L. That's all. So that is a point to be noted. This conclusion is important. What is your original problem? Original problem is solve equation number 6. That is the original problem. How will you solve? Schematically, I can write it down as L inverse, but L inverse must be corresponding to some kind of integration. That integration should act on the original function, and then you perform the differentiation and get the answer. Then the answer should be the y of x. So y of x is the quantity that is coming into picture. And remember, since the right side is not equal to 0, this is an inhomogeneous differential equation. So our conclusion is that if you want to get the solution to the differential equation, then the solution is given by, or solution is given in terms of green function, and green function itself is coming because of the operator. So remember, green function should correspond to operator, not for the differential equation. You can change the differential equation to something else, but this operator should not change. Only what freedom you have to change is only the right hand side. So this is a point to be noted. You can change f of x to g of x and put a g of x here, no problem. You put sine theta here, you put a sine x, you can put a sine x and finish the problem. After that, you change it to cos x, and here also you put a cos x and do the problem. So that is allowed. But the operator itself should not be changed. In case if you change the operator, the g will be changed to something new value. It is called another green function. Okay, so that is why it is called the kernel. So kernel will keep changing when operator changes. So the question fundamentally comes, why this method is first of all interesting is that the reason why this method is interesting is you have the freedom to change the right hand side. If you change the right hand side, the method is same. Method is same, and this equation is still valid. Equation number 7 is still valid even if you change the right hand side. That means you change this particular cos x to sin x, means this also you delete and put a cos x to sin x and perform the integration, you get the answer. So in that way, green function method is considered to be somewhat better method when compared to some other method. Any other method you learn, what happens is when you change the right hand side, you have to redo the problem from the beginning. So that trouble is not there in this method. So once you find the green function, you can keep on changing the right hand side, and then you simply perform the equation number 7 integration and get the answer. So that is the reason why green function method has gained some popularity, and that is also one advantage. Okay, that's all about it. But however, if you are doing all the steps, you'll feel that a considerable length of work is there. You can't get it in 2-3 steps. Okay, so you'll have to spend a considerable amount of time and then do all the steps. Okay, now the methodology is clear. So now I would like to next step I will write down. So this is one part of the understanding. The next thing is, where is Dirac delta function? Till now Dirac delta function didn't come. So therefore I will now write down from where Dirac delta function comes into picture. So you already know what is the definition for the Dirac delta function. So whatever you know that, I will write down that, right? The Dirac delta function is defined by the standard relation that you have an integral of the Dirac delta function x minus x prime. Then you have multiplied by a well-behaved function f of x prime, and when it is integrated, I will get f of x. So this is the standard definition or defining equation for the Dirac delta function. And once you have this equation, what we are going to do is we are going to compare this with equation number 7. You have equation number 7, right? I want to compare. For the purpose of comparison, I want to copy equation number 7. So let us write side by side, then only it is easy to compare. So I want to simply copy the equation number 7 here. So g of x comma x prime, then multiplied by, you have f of x prime multiplied by dx prime, and then equal to, you have y of x there, write that y of x here. So it is the same equation number 7, but I'm writing side by side so that it is easy to compare. And our original problem you should not forget. So we are interested to solve equation number 6. Remember that. Okay, now keeping these two things, what you can do? So let us write down the original differential equation which we are interested to solve. So all the things are together now. Okay, now we are going to make a comparison and then write down a conclusion here. If you are going to take the L operator on both sides of equation 7, how it looks like? Simply attach L there, that's all. You simply attach L on both sides. That's what I'm writing. And that's all. And we can simplify this. So if you simplify this, I take L operator inside. So take the L operator inside. Then rest of the thing is same, f of x prime dx prime, same thing, no changes. That will be equal to the right hand side f of x. Okay, so the point to be noted is that you only applied L operator. Here you attach the L operator and similarly attach the L operator here. So what is L of y of x? If you attach L operator here, what happens? L of y of x. But what is L of y of x? F of x. So that's why we have written here. That is clear. Now the L operator will go inside. Now the question is that how it will go inside, you already know. The integral, this particular integral is on the primed variable. This is primed variable. Whereas the L operator, namely the derivative operator, will operate unprimed variable. Therefore, where is unprimed variable? You don't have unprimed variable here. Therefore, L operator will not operate on f of x prime. Therefore, I am closing the bracket here. F of x prime is not included. Even if you include it, doesn't matter. It will not operate. That is the meaning. So, L operator will operate only on the x part of the green function. So, I combined like that. And f of x prime and dx prime simply comes here. That is equal to the same right hand side that you are going to have. So, the step is now clear. So, the reason I will write down, the reason is L operator will operate on x only. Integral operator will operate only on x prime only. Okay, so let us give some number. I don't know. Yeah, 8 is there, 9 is fine. Okay, that 9 looks fine. F of x is same f of x dx prime I'm copying. So there is no need to worry about any change in the symbol. So whatever that was there step by step, everything is there in one screen. And you'll have to focus the attention on the delta function there and then L operating on the G. These are the places where you have to focus your attention. And if you focus your attention and compare this equation 8 and 9, okay, we are going to compare equation number 8 and 9. That is why I have highlighted in green color. We are comparing the equation number 8 and 9 and especially focus your attention on the highlighted region. What we can write? We can write like this. So you compare both. Okay, the screen is going outside. So compare both. You have these two, right? That green color highlighted one, they should be equal. That is what you understand. So therefore, L operator operating on the G should be equal to the Dirac delta function. And that is your equation number 10. So what is your conclusion? We got the requirement here. So I will highlight it. What is now understand from equation number 10 is green function is related to Dirac delta function. So that is the conclusion. Our conclusion is the green function to the operator L has a connection to the Dirac delta function and the solution will give you that. Okay, so you go back and see what is your original problem. I mean, equation number 6, right? So that equation you remember because that is the equation to be solved. As an intermediate step, we got this expression. So equation 6 you should not forget because that is the one we are going to solve. And what is our conclusion as an intermediate conclusion is the green function which is going to help you to solve the equation number 6 is given by this expression. What expression? Y of x equal to, you already have it, right? I'm just copying this one. Equation number 7. That is the equation. I'm copying it once again because everything should be in one place. You can see integral of g of x comma x prime f of x prime dx prime. So is this point clear? This is the conclusion. What is the conclusion is you have L operator operating on green function is Dirac delta function. Solve this equation and then get a G. After getting G, what to do? That is a question. No, here it is. The answer is there here. You get the G and then substitute here. And G multiplied by f of x prime, if you integrate, you get the solution to the given problem. That is the meaning. Solution to the given problem is equation number 6. Can be solved by using the green function, and the green function will be obtained from equation number 10. And the compulsory or a compelling point to be noted is that the right hand side of this equation should be always green function, should be always Dirac delta function. This cannot be changed. So that is why I have derived this. This is true for any differential operator L. Any problem you take, right hand side you have to dump a Dirac delta function and solve this. That solution is called green function. That green function you put it here, and then you can now ready to solve the original equation number 6. So that's the story. Okay, so if you are taking certain exercise and then solving, you can feel how much lengthy work you will have to do, but at least in this lecture you are learning the overall methodology. So this particular method can be applied to an ordinary differential equation, or it can be applied to partial differential equation also. Both of them, it's okay, it's applicable. That is the first point I would like to tell. And the second thing that I would like to tell is that in particular we are interested in Poisson equation in electrostatics. Mathematically, okay, so many differential equation you can apply, but in electrodynamics, what is our interest is that we are interested to solve the Poisson equation in electrostatics. Where is that equation? We are here it is there, right? This is the one, the highlighted region. So I will try to overwrite once again. I don't know, it may come nicely. So del, you have that equation, right? The so-called, you have this del square v, etc. Okay, that is the Poisson equation. So now you understand. So now you understand how the equation number 5 is there, and okay, that's all about it. And here is the equation number 5. And see this. Now you understand what is this. This is our original equation to be solved. You delete the right hand side and put a Dirac delta function, and then solve this equation. If you get the solution, that is called the green function, and that green function you are going to evaluate the electric potential. That is the story. But what is interesting about the electrostatic problem, namely Poisson equation problem, is that you don't have to struggle to solve equation number 5. That is the interesting thing. You don't have to struggle to solve, but instead 1 divided by r minus r prime itself is the green function. That is what we have been from the beginning we have seen. 1 divided by r minus r prime I already highlighted, right? That is going to serve the purpose of the green function. That means even if you struggle to solve this, we will be getting this. So in that way, at least solving the electrostatic boundary value problem would be somewhat simple, because green function to the Poisson equation is known to you. Known to you means 1 divided by r minus r prime. This is the important conclusion. Our conclusion is green function to the del square operator operating on the Poisson equation, appearing on the Poisson equation, is already known to you. That is nothing but 1 divided by r minus r prime. So using this, one can proceed further to obtain the green function based solution, what you call the general potential. So this is known as the generalized potential for a given electrostatic boundary value problem in terms of green function. Without green function also you can evaluate. Some methods are there, but this is one most popular method. So that is why I'm explaining. So okay, so this must give you a fairly good account on the application of the green function to electrostatics. But doing a generalized problem like arbitrarily, we can take always some example from mathematical examples. Without limiting to electrostatic, we can always consider some problem and then solve some differential equation using green function. But that would be an appropriate lecture for mathematical physics course, okay, rather than electrodynamics course. So with reference to the electrodynamics course, at least solving the Poisson equation would be appropriate. So to this extent, this introduction would be sufficient for you. Okay, so we will see other than this particular method, namely other than the green function method, can you use some other method, something like method of separation of variable? Can you use for the solution of this same Poisson equation? That is a question, and we are going to see the answer to be yes. And we will see that method of solving the Poisson equation, that is also called electrostatic boundary value problem, and that we will see in the next class. Once again we will do in spherical polar coordinate system. Okay.